Hello, everyone. Welcome to my presentation of Reconfigurable Array for Analog Applications. My name is Zi Chen. I'm a PhD student at Drexel University, and my advisor is Dr. Yanis Savidis. My talk will start with Introduction to Field Programmable Analog Array. The field programmable analog array is an array of analog devices. Routing switches are usually added to configure FPA into different applications. The bit stream is used to program the FPA fabric. By implementing analog designs on the FPA, the designer is able to prototype an analog design faster. Other advantages include flexibility in testing, reduced design cycle, and secure analog components. On the right side is the design flow for the FPA. Start with the analog baseline design. A bit stream is generated according to the placement and the routing algorithms. Then the bit stream is fed into the FPA fabric, and the FPA is programmed into various analog design. So to improve the performance of the FPA, we want to improve the performance in both the bandwidth and the flexibility of the FPA fabric. We target different types of analog circuits and applications. We want to improve the flexibility of individual caps, and we want to increase the bandwidth while maintaining the flexibility. To target different types of analog circuits, we target the filter, amplifier, oscillator, and the switch capacitor circuits. To improve the flexibility of individual cap, there are no fixed topology within the cap before programming, and the homogeneous architecture fit a versatile design. To increase bandwidth while maintaining flexibility, we provide a hybrid routing strategy between caps. Switchless routing network is proposed to provide high-frequency filtering. The global routing switch array enables various closed-loop systems. Next, I'd like to talk about the architecture of the FPAA. According to the functionality of the cap, there are two types of cap array, support both differential mode and single-ended mode operation. There are also 7 input and output ports, allows direct access to the input or output of the cap in each column. There are 418 programming keys in total for this FPAA. On the left side is the architecture of the differential mode cap. The wisdom behind is that, as we can see on the right side, we can use S1 to S5 to configure transistor M1 and M2 into 4 different topologies. The similar concepts can be applied to PMOS transistors as well. The remaining switches S11 is used for common mode feedback, and S12 and S13 are used to turn off the cap completely. The single-ended mode cap has the same concept of programmable transistor pair. Switches S11 to S14 are used to isolate input ports, and S15 to S18 are used to turn off the cap. In order to rapidly implement analog design of FPAA, we propose a synthesis flow for the FPAA. We first determine the configuration of the caps, then the cap bias and the global feedback network. Then we generate a list containing all the configuration data. Finally, the configuration list is compiled into an ocean strip for simulation. Now I'd like to talk about some implemented design on the FPAA. The first one is the differential mode ring oscillator. The cap is programmed into single-stage op-amps. The global routing network is used to configure feedback between A1 and A4. Due to differential mode operation, we allow for even number of stages as well. Hence, the FPAA can support 3 to 6 stages ring oscillators. The simulation result shows the transient simulation of ring oscillator at an oscillator frequency of 207 MHz. On the right side shows the tunability of the oscillator frequency. Another example is the second-order backward filter. By turning on and off caps in parallel, we can control the transconductance of GM1 to GM4. The equation shows that we are able to tune in the peak gain and the center frequency by controlling the GMs. The simulation result shows that the backward filter has a center frequency of 1.5 GHz and the tunable peak gain from -10 dB to 8 dB. The last implementation I want to talk about is the frequency divider, which consists of 2 caps. Each cap is configured into dynamic latch. The global feedback network is used to form the feedback between D1 and D2. The simulation result shows 4 outputs with 19-degree phase shift. In conclusion, FPAA array supports both differential mode and a single-ended mode operation. FPAA cap topology provides various options based on basic analog building blocks. FPAA provides programmability for larger analog systems. Area of FPAA core is 0.1 millimeter square in a 65 nanometer process. The characteristic power consumption is approximately 24.6 millivolts. The implemented design includes bandpass filter, divider, and ring oscillator. Thank you.